Good morning, everyone. Okay. Good morning, everyone, and welcome to the second day of our PIA conference. To start us off, we have Professor Linus Huang from the Hong Kong University of Science and Technology. So please join me in giving him a very warm welcome.
So thank you for being here with me and to give me this opportunity to share this research. So I typically approach AI ethics from a broadly philosophy of science perspective, and this project's no exceptions. And this is kind of a work in progress paper that come out of interdisciplinary collaboration with a computational neuroscientist. So as I said, it's a work in progress. So I really appreciate if you can give me some feedback, especially some kind of concrete example to kind of help illustrate the more abstract arguments that I will focus on. So one fun fact is this background images is actually generated by DALL-E. So what I do is I just put in the entire manuscript into DALL-E and say, generate the image that capture the essence of this paper. I think it did a pretty good job, and we'll see if you agree with me at the end of this paper. So the focus today is generative models. And assume you haven't just wake up from a one-year coma. You probably know what it is and probably use it as well. And some of the famous generative model are, for example, transformer architecture that's behind the ChatGPT or Google's Gemini. They're particularly good at language processing, but there are also diffusion model, which is behind stable diffusion and DALL-E, which is much better at image generations. But today, what I will focus on is this generative adversarial network or GANs model. So this is actually a very widely used model. It's probably behind some of your favorite social media filters, but it was just not widely known in the public. And it consists two separate neural networks, one a generator and one a discriminator. And they were trained simultaneously through some kind of competitive process. That's why the adversarial in the name. And they're also very good at image generations in particular. So I've chosen to focus on GANs today for two reasons. One is because this technology is older. And when I mean older, it's like 6 years old, right? But in AI, 6 years is like ancient history. So a lot of work has been done on it, and we kind of know the mechanism relatively well and how the bias is produced relatively better. It's also a simpler model, so we can kind of know the parameters and what's going on there more clearly. But more importantly, the lesson we can get from analyzing GAN should actually generalize to all generative models. So let's focus on GAN today. So as we know, generative model has the best rep these days. If you have paid attention to the news last couple of weeks, Google Gemini released a new update. And partly because Google's attempt to try to increase diversity, right, in the image generation, it ended up generating very historically inaccurate images, such as Black and female Nazi soldiers. And Google shut down their image generation capacity almost immediately. But what surprised me is actually not this. So what surprised me is the massive public attention on this particular issue, because I think there are much more known issues that were way worse and deserve our attention more. So let's just look at one paper from last year by Bianchi from Stanford. So this study prompts stable diffusions to generate images of different professionals without giving them the gender and race identity. And one example we can see here is the images for software developers are exclusively white, even though they only constitute just under half of the software engineers in the US. And another example is the flight attendant images. Again, we can see clearly it's all female. Again, despite the fact that only about 60% of flight attendants in the US are female. And importantly, these biases cannot be eliminated with more careful prompting, right? So here are some of the examples of trying to prompt more carefully, but still result in very, very biased representations. So this is really a major setback on representational fairness. So I hope you agree with me, this deserves much more on the headline compared to the Google Gemini problems. And if you think this problem has been fixed, bad news, it hasn't, right? So I tested myself by asking DALL-E to generate 10 images of philosophy professors. And here is the problematic result. So first, you can probably see that DALL-E doesn't know how to count. So he gave me 12 images instead of 10. But more importantly, these images all depict white and male professors exclusively. And this is my first and only attempt. So followed by that attempt, I then prompt DALL-E to generate 10 images of Asian philosophy professors. Again, these images depict only male professors again, but they also show other stereotypes, right? So it's just some of the example. First, it kind of depicts Asian philosopher as kind of engaging some kind of meditative practice. That's what we do. It also assumed that Asian refers to just East Asian, right? So ignoring the rest of Asia pretty much. Then I followed again by prompting, generating 10 Asian female philosophy professors. So again, a lot of problems here. And some of the problems are, for example, most of the female philosophers here are extremely young, and they seem to be engaging some kind of learning instead of teaching or like actually doing philosophy, right? So I've given enough example of what I call the generative bias here, but a proper definition here. So generative bias happens when a model systematically generate data or images that systematically diverge from some normative standards. And the standard here could be moral, could be social, could be statistical. So for example, when they underrepresent, misrepresent, or stereotype certain social groups. And generative biases are distinct from predictive bias, that is bias prediction or decision from predictive models. They're also distinct from dataset bias, that is bias that exists in the training data. So while existing literature has almost exclusively focused generative bias that reflect well-known societal bias like sexism, racism, this really underestimates the moral risk these models can create. So in this paper, what we will argue is that generative models such as GAN can produce unexpected and uninterpretable generative biases. So these biases can systematically misrepresent and underrepresent minoritized groups. However, they don't result from human biases only, but really can arise intrinsically just from the machine learning process itself. As a result, they can be quite epistemically opaque and undermine our ability to debias them. So this greatly amplifies the moral risk associated with GAN and other generative model that really hasn't been focused on in the empirical literature. So what I will do in this talk first is to introduce the GAN model and clarify some of the key concepts such as mode collapse. Then in the main argument, what I will mainly do is spell out the full causal consequences of mode collapse in creating these uninterpretable, unexpected biases. Then I'll come to refute potential criticism that these biases may not have moral significance. Then finally, I work out the epistemic and practical challenges these biases pose and emphasize the heightened moral risk associated with generative models in general. So let me now turn to a brief introduction of GAN. So I could go through this point kind of in a very dry way, but instead, let me show you a much more interesting videos. So let me just try it anyway. Um, so a generative adversarial network, again, composed of two neural network, right? So there's the generator and the discriminator. So in the beginning, this is not possible. Why can I hide the ads without showing the screen? Okay. So the key idea is there were two networks. One is the generator network and one is the discriminator network. And in the beginning, their parameters were kind of randomly initiated, right? So they don't do anything because they don't know anything. So what we do is we start by feeding like random noises to the generator data. And because it doesn't know anything, it will create noises, right? And the same thing with the discriminator network at the bottom that we couldn't see. So it's a discriminator. So what it does is it can, we input it either output for the generator or input it with images from the data set. So what the discriminator do is it will make a judgment. Is it a true image or is it a false image? Is it a true image from the data set or is it a synthetic image from the generator? And in the beginning, because the discriminator also was randomly initiated, it has no knowledge. So it's just kind of making a random guess, right? So sometimes it would say the image from the generator is true. Sometimes we'll say it's false. It's all kind of random. But what happened is the learning part, right? So when it judged the images from the generator as false, it has made the correct decision. So we won't give it any error signal. But when it judged the generator images as true images, then we'll give it an error signal, right? So this learning will help discriminator kind of start acquiring the statistical patterns from the data set. And similarly, the learning for the generator comes kind of indirectly from discriminator, because whenever discriminators say that, oh, the images you generate is fake, whether it was a true answer or not, it will give a learning signal to the generator. And eventually, the generator start acquiring also the statistical pattern from the data set. And through this kind of competing process, they both starting getting better and better, right? Because as discriminator get better, generator have to get better to fool it. As the generator get better, discriminator have to learn more from the real data set to be able to distinguish the fake data and true data, right? And then once the discriminator get better, it forces the generator to get better. So through this kind of competitive processes, they both learn the statistical pattern from the data set. And that's how the game works eventually. All right. So let me just turn to the concept of modes, which would be quite important for the rest of the paper. So the term of modes really are just used to kind of pick out the statistical patterns in the data set. We can think of each mode as referring to one common feature combinations, right? So just consider one simple example from this data set that consists of athletes' heights and weights. So we can visualize the whole data set with this 3D landscape. So there are several hills here. Each hill represents a mode. And the taller the hill is, the more athletes share this particular weight height combinations. And we can call the taller hill here majority mode and the shorter hill here minority mode. So what is majority, what is minority is always relative. So when GAN successfully learn the data set completely, its output will replicate the entire landscape. And the first source of generative bias will be just from dataset bias, obviously. And this is essentially this bias in, bias out that's typically discussed in the predictive model, but now in the generative model context, right? And the reason behind this is because GAN aims to replicate the entire statistical pattern in the data set. So if the minority mode is a result of wrongful underrepresentations of a group, GAN will, of course, also replicate the exact bias pattern. But there's a second source of generative bias, which is from mode collapse. So mode collapse happens when the GAN fails to learn certain modes or patterns. So as a result, it also fails to kind of produce them in its output. So I will call the generative bias from mode collapse GBM for short. And this will be the main focus of the rest of the paper. So again, coming back to this similar example, in this case, mode collapse happened to two of these minority modes. And as a result, GAN also failed to replicate them in the output. And what happens, the output underrepresents these associated athlete groups. So before we move on, let me emphasize a few actually key themes that will recur throughout this paper about mode collapse. That's not really articulate explicitly or even properly in the empirical literature. So first, mode collapse is very likely to happen when model capacity, training data, or training time are finite, which is practically always the case, right? And the larger the gap between the model capacity, time, and training data, and the phenomenon it aims to capture, the more pattern the model will have to miss ultimately. But it is actually very difficult to predict which modes will collapse because this is essentially due to the stochastic nature of machine learning. So for example, when we initiate a model, we do it almost always in a randomized manner, right? So the random initiation of model parameter will affect the eventual learning trajectory and like affect also the final behaviors of the model. So because of the random initiation, we kind of cannot predict what mode will collapse exactly, even though we know that it will. So I call this the stochastic nature of machine learning. And the second thing is mode collapse affect minority modes to a greater degree. And this is because machine learning models by default just favor majority modes. Why? Because majority mode by definition means it contains more data points in the data set. And when there's more data points, it just means better learning opportunity, more learning opportunities, right? So that is why mode collapse affects minority modes kind of systematically. But because human and model kind of perceive the data patterns from very different perspectives, and this divergence kind of will present a significant epistemic challenges, which I'll come back to later in this paper. And finally, mode collapse, while receive much more attention in GAN, it is theoretically should happen to all generative models. Again, this should be obvious because all generative models share the two problems I just mentioned earlier. right? So they all share this propensity to collapse minority modes. So I will call this tendency for homogenizations in favor of majority modes. Okay, now let me illustrate a few different types of generative bias using a scenario based on empirical literatures. This illustration will help you kind of get a better understanding of how mode collapse works. But it's also important to keep this example in mind because it will help you anchor the more abstract argument later. So let's start by imagining a company that uses GAN to produce syntactic images of engineers for their websites or marketing materials. So this training data is scraped from university in the US, particularly from the engineering faculties. And because white and male engineers already overrepresent compared to the actual demography of engineers, right? So more male and white engineers are hired as engineering faculty compared to like the broader engineering community. So the data set is already in a way statistically biased in terms of race and gender. And based on this training data, GAN models will end up producing generative biases leading to further underrepresentations of minoritized engineers and amplify the stereotyping of engineers of all social groups, as well as misrepresenting minoritized engineers, including introducing masculinized facial features, skin whitening, or poor image quality. So let me turn to how mode collapse leads to these different biases. So the first one is amplifying underrepresentations of minority group. So let's just consider this empirical finding. So we start with a data set with 20% images that's recognized as female engineers. A figure, as we said, already underrepresent them. But when mode collapse happens, GAN will end up generating less than 7% of images that are recognized as female according to human test subjects. So why does mode collapse lead to these results? This is because female engineers are minoritized in the data set. So various stereotypically feminine facial features will be associated with minority modes. And when some of these minority modes inevitably collapsed, it would decrease the representations of the associated feminine facial features in the output, which then lead to even fewer generated images that will be later recognized as female by the human test subject. So mode collapse will not just reflect, but amplify the underrepresentations. Second, GBM also reinforce stereotypes for all social groups, right? So let's take one dominant stereotype, such as the nerdy-looking male engineer as an example. So these stereotypes, because it's a common pattern in the data set, will be associated with many majority modes, right? So again, when GAN experience mode collapse, they will fail to mostly retain minority modes. And this will lead to the overrepresentations of majority modes in the generated data. And as a result, they will generate more images of nerdy-looking male engineers and reinforce the stereotype. And finally, the third type of GBMs misrepresent. So when, again, minority collapse, so for example, when minority collapse, minority modes that's associated with female engineers collapse. Generated images will tend to have fewer stereotypically female facial features, right? So some images that's ultimately judged by the human test subject to represent female persons will still, some of them will exhibit more features that's kind of stereotypically considered masculine. So as we can see in the two images on the slides, they are recognizably female, but with various facial feature kind of masculinized. So if many generated images are like this set of images will end up misrepresenting female engineer as a group by making them kind of in general look more masculine. So kind of just wrap up the example. We can see that all of them kind of illustrate this GAN's tendency to homogenize their output in favor of majority modes. So what I've done is I reviewed a bunch of current literature on how mode collapse lead to a variety of generative biases. As I emphasized, most of the empirical literature really just focus on generative bias that's reflecting existing societal biases. But this really failed to capture like the full problem generative bias poses. So what I do in the next section is I will work out the full causal consequences mode collapse and demonstrate the real danger of generative bias that are rarely acknowledged in the literature. What I will show is that generative bias discussed previously really are just special cases of a much more general phenomenon, right? Specifically, GBMs can reflect and exacerbate unknown dataset biases, and they can also result from an imbalanced dataset with no dataset bias at all. They can even result from a dataset that's theme balanced and unbiased. Moreover, their patterns can be quite difficult to interpret. So what happens is GAN will end up generating enormous amounts of unexpected and uninterpretable generative bias that has the potential to cause harm. Let me argue for each of these camps. So first, generative GBMs can reflect and exaggerate unknown biases. I hope this should be quite obvious because mode collapse can happen to minority modes that's associated with dataset or societal biases, whether we are aware of them as such or not, right? And this is because how the nature of mode collapse and the process of mode collapse just kind of work independent of our knowledge or epistemic perspective. And the second claim, GBMs can result from an imbalanced data set that has no dataset bias at all. Here, imbalance refers to an uneven data distributions across some dimensions of in the feature space, for example, race or gender, or even like hair color or something like this. And importantly, imbalance need not reflect any existing societal bias or dataset bias, right? Because, for example, a statistical unbiased data set that reflect real-world racial distribution can still be imbalanced. This is because this data are not evenly distributed along, for example, different categories along the racial dimension, right? So as long as the data was not evenly distributed, it is unbalanced. So what happens is that as long as there are some imbalances, there will be minority modes. And if there are minority modes, that you will generate a variety of GBMs coming out of mode collapse. So here, again, we can see the three things I kind of mentioned earlier, kind of recurring here, right? So generative bias can come out from the process of machine learning itself. It doesn't really depend on human knowledge, epistemic perspective. They kind of can function independent of that. And we'll see some of the things kind of recurring again. So let me move on to the third claim. The GBMs can emerge from a data set that's theme balanced. So one reason behind this is because the concept of a balanced data set is always relative to the standard a stakeholder adopt. And this is because it's practically impossible to balance all dimensions in the data set, right? There are just way too many dimensions. So what happens typically is we try to balance some dimension that we consider important. So for example, a dimension regarding binary gender, right? But such a balanced data set will still contains a lot of imbalance along features that weren't picked out by the stakeholder for balancing. And the second reason, and even if we put the first issue, which is already tricky enough, aside, we will still encounter the second problem, right? So a data set that's perfectly balanced from a human perspective is unlikely to be balanced from a model's perspective. This is because the feature model used to process the data are typically very different from the concept we use to describe the data. For example, when a human use concept to describe a face, we use concept like facial hair color, maybe the shape of the eye, stuff like this. But machine learning typically will invent features through the learning process, and they use those features to make categorization or generation. And these features are often uninterpretable. That is, they do not correspond neatly with the concept we use to describe the data, right? But minority modes or mode collapse should really be defined over the feature the model used instead of the model we use to describe the data, right? Because mode collapse is what machine do, right? It's kind of independent of perspective, again. So again, the data that's perfectly balanced from a human perspective will still contains a lot of imbalances again. So again, like putting this already tricky issue aside, mode collapse can still happen in a perfectly balanced data set from machine's perspective. That is, this data set will just contains no minority mode. So essentially there will be mode, but everybody's equal. So there's a mode majority, no minority, right? So as we discussed earlier, because mode collapse is almost inevitable in the practical context. And this is because of the gap, again, between the limited capacity of the model and the complexity of the phenomenon it aims to kind of capture. So you will have to miss some pattern, even though we cannot predict which pattern you will miss ultimately. So given this gap, again, mode collapse will just happen. So due to these three reasons, even the data set that was deemed balanced for any reason will still generate a large number of GBMs. So finally, GBMs can be interpretable, at least at some level of description. So we call a generative bias interpretable if we can explain its pattern of underrepresentation or misrepresentation with intuitive concepts, terms, or features our relevant audience could understand or grasp. And there are two main reasons why this happens. So first is what we already kind of mentioned, right? Because the collapse mode may be associated with machine learning invented features that are itself uninterpretable. And the second reason is that because of stochastic nature of machine learning, the pattern of collapse mode will be somehow random and won't follow the pattern that we expect to see in the natural world or the pattern we are familiar with. Because this pattern in the natural world happen for reasons, right? We may not be familiar with, but there are historical contexts why they happen. And if we are aware of them enough, this pattern become familiar, right? It kind of become part of our interpretive resources. But because machine learning in building this completely random processes, the pattern won't follow our familiar pattern. So let's just consider a simplified example that illustrates only the second point. So imagine a data set that with a subset of minority modes that's related to Asian engineers collapsed. So in this case, only some of the facial features associated with Asian engineers go missing. But the pattern of the missing feature will be partly random, right? So these will still lead to the underrepresentation of Asian engineers, but its pattern will not mirror what we typically see in the world. So what we typically see in the world is all Asian features will be somehow underrepresented, somehow equally to some similar degree, right? Or in some cases, we'll be missing some facial feature that kind of associated with specific subgroup. For example, maybe Vietnamese engineer or Taiwanese engineer. But when mode collapse in GAN, the pattern will be partly random. Won't follow this category or pattern that's kind of has some kind of historical origin or we are familiar with. All right, so let me sum up the main arguments. So we have shown that generative bias are not just a reflection of biases that reflect societal bias. They can emerge even from an unbiased or balanced data set, and they can present uninterpretable patterns. And this is due to the three themes that I mentioned earlier. First is the tendency for homogenization in favor of majority modes. And the second, the discrepancy between human and model perspective on individuation and existence of modes or minority mode specifically. And it's also due to the stochastic nature of machine learning that make patterns of mode collapse quite unpredictable. So this again highlights how GAN can produce an enormous amount of unknown, unanticipated, and uninterpretable bias that could potentially cause harm. So let me stop here to counter a potential criticism at this point. So one critic may say, yeah, I agree with you, GAN may generate this enormous amount of unexpected, uninterpretable generative bias. But are these biases morally significant? To address this, let me focus on how these generative bias can pose representational and allocational harm. So let's first turn to representational harm. A representational harm happens when a system represents some social group in a less favorable light compared to others, or demeans them and fails to recognize their existence altogether. So one famous example that's well documented is that when one Googles the term Black girls, it tends to return overly sexualized images compared to white girl, for example. The philosophical literature focusing on representation harm is still really emerging, right? So we're gonna kind of do our analysis, borrowing resources from literature on wrongful discriminations and cultural stereotype instead. So how does representation harm? So first, the first way it could harm is through reinforcing problematic social hierarchy. So for example, the underrepresentation of female engineers can have the potential to further reinforce their inferior status compared to male engineers. We should know that the harm here depends on the actual causal effects that's produced by this underrepresentation. And there's a second way representation can harm. So it is through the expressing of disrespectful or denigrating social meanings. So for one example, the underrepresentation and misrepresentation of Black engineers can express things like, oh, they do not deserve accurate representations or adequate recognition, right? So here's the harm depends on the representation's social meaning, which is the best interpretation in the particular culture at a particular time. So importantly, the social meaning here does not depend on the intention or motivation behind the creation of the representation. It also does not depend on the specific effect of this representation on the individual or any particular individual's interpretation of it. You will be like, overall, what's the best interpretation considering the social circumstances of the time, right? So this distinction will end up being very important for the argument later. So the previous discussion are kind of drawing from generative bias that reflect well-known societal bias. So let me now generalize it to other GBMs we discussed in the main argument. So first, for GBMs that reflect unknown dataset bias or societal bias, it should be clear that more significance are there, right? Because whether a GBM causes representational harm does not depend on our awareness of the relevant societal bias at all. So for example, racial stereotypes are harmful or were harmful, right? Because they reinforced problematic social hierarchy and they expressed disrespectful social meaning, even when the society weren't aware of racism as such. How about the new GBMs that do not mirror existing societal biases? So these GBM typically arise from mere imbalances in the data, and they can affect either already existing social group or they could affect machine learning invented social groups. But here, I think it should be relatively uncontroversial that some, but not all of them, can cause harm, right? And one of the major sources of harm is this further homogenizations in favor of majority groups. So for example, the new underrepresentation of an existing group can express insufficient recognition and lead to their marginalization. In addition, new misrepresentations say when the GAN create images of female Asian engineer that appear whiter and more masculine, it can still express disrespect, such as suggesting that, oh, these groups do not deserve equal representational accuracy, or the way of being is white or male. So finally, let's consider the new GBMs that target groups that's new and invented by machine learning process itself. It is slightly tricky here because these groups don't fit into our existing social hierarchy and they are not associated with kind of existing social meanings, right? So I think it's fair to say the probability of harm is slightly lower here. But if these biases become widespread in the society, they have the potential to establish new social hierarchy and new social meanings. So over time, through what we call the looping effect, right? They can actually gradually build up the conditions to cause harm. So finally, all of GB generative bias that we have discussed can be uninterpretable to some degree. But is interpretability necessary for harm? So let's consider, again, a concrete example that we draw from empirical literature. So this 2022 paper showed that generated images of minoritized group tend to have lower quality judged by the human test subjects. And we argue that this is due to a form of uninterpretable misrepresentation. So recall our last example where images misrepresenting female and Asian engineers because they represent them in a way that's whitened and masculinized, right? And now imagine this case just in an uninterpretable version. So these images will still be judged to represent female Asian engineer, but they will possess features and patterns that kind of defy our expectations. So what happens is these images will appear off, like they will be off in some ways, right? But we couldn't really articulate why. And we argue that this is why the test subject end up judging them to be of poorer quality. But despite being uninterpretable, this type of misrepresentation can still reinforce socially problematic hierarchy through the effects of privileged representation of majority groups. And it can also has the potential to express similar disrespectful social meaning, because again, social meaning does not depend on an individual's interpretation of it. Finally, let me just briefly talk about the allocational harm. So allocational harms can happen when people belongs to a particular social group, are allocated important resources or opportunities unfairly. This is widely discussed in the predictive model literature because they can be used to distribute resources, right? So for example, in the criminal justice system or loan approval systems. So one famous example here is that research shows that facial recognition models developed by Apple and Microsoft tend to make more errors and have lower performance when it comes to minoritized group. And this is because their training data systematically underrepresent them. And as we've seen in the generative model context, less training model leads to less performance for sure, right? And because one major application of generative model, especially for GAN, is to produce synthetic data to train predictive models. GAN will have the potential to produce allocational harm as well. Let's here really just consider the most extreme case, right? So imagine a game may produce training data that misrepresent and underrepresent a machine learning invented groups. And when these images are used to train a predictive model, they will cause less accurate performance, like predictions about this group in particular, which then leads to unfair distribution of resource when it comes to these machine learning invented groups. So in short, I've addressed this potential criticism in question: are unknown, unexpected, or uninterpretable generative bias morally significant? And our answer is yeah, some of them. And one source of their harm comes mainly from machine learning's tendency for homogenization in favor of majority modes. Now, let me turn to the final section of this paper, which is the epistemic and practical challenge posed by these generative models. Here, I will show that we really don't have the proper epistemic resource to detect and evaluate generative bias. And this makes it very difficult for us to assess the moral risk of GAN models and to debias them as well. So first, consider the challenge of detecting generative bias. So what we do when we try to detect a generative bias is that we'll begin with our background knowledge of how a related societal bias look like, right? So for example, how racism looks like, and infer what the biased image will be roughly like in the output. And then once we have that idea, we can design the measurement for the related, say, facial feature for detection, right? But the problem is for the unknown and unexpected generative bias, we don't have such social knowledges. And because mob collapse can happen to any of the feature dimension in this massive, large dimensional space in GAN, without this knowledge to work as a guide, to kind of anchor the search, the detection of bias become intractable. There's no amount of resource we can do to kind of check individually all these dimensions. Moreover, even when we do have the relevant knowledges, our detection capacity is still limited because there are these uninterpretable generative bias. Because these uninterpretable biases have patterns that do not align well with our expectation, background knowledge, or interpretive resource, really. So we couldn't really use them to guide the design of the reliable measurement for detection. And that's why, like, even for generative bias that reflect social, societal biases like racism, our detection was still limited, right? Okay. And the challenge for detection has a direct impact and practical implication for debiasing them. And this is because one way to debias again is to detect and remove the bias output. So the same problem applies here. But even for other debiasing strategy, for example, we can curate the training data, right? For example, try to balance as many dimensions as possible. Or we can design algorithms to reduce mode collapse. These two strategies will encounter very similar epistemic challenges, or ultimately they would involve detection of a bias output to work properly. Just briefly talk about it, because curating training data is impossible, right? You cannot curate to balance all dimensions. So eventually you need some anchor to guide the balancing. So that's kind of roughly the case. And eventually you need to look for the output because some bias will happen. The same thing with the designing algorithm to reduce mode collapse, because it's always a trade-off. When there are fewer mode collapse, they would generate other more biases. That's just kind of intrinsic to the trade-off between learning the majority pattern reliably and learning something that's off. So when you learn something that's off, you end up creating other biases, then you need to debias the output. So that's kind of a rough reason. Eventually, all comes back or depends on detecting bias in the output. Okay. And finally, in order to evaluate the potential moral harm of a generative bias, we also need to know how a specific bias, for example, related to racism, will interact with the social and psychological structure. But again, we don't have the relevant knowledge when it comes to this unexpected, unknown generative bias. So it makes it very difficult to evaluate the full moral risk of GAN. Let me sum up the talk. So I have discussed the causal, epistemic, and moral consequences of mode collapse. So GAN do not merely produce misrepresentation and underrepresentation that reflect and exacerbate societal biases as most of empirical literature suggests. It can actually produce many, many more unexpected and uninterpretable generative bias due to mode collapse. And this generative bias can be morally significant and systematically impact minoritized group. They can also challenge our ability to detect, evaluate, and debias them. As a result, the moral risk of GAN is greater than commonly acknowledged. Finally, our analysis for GAN applies to other generative models. This is because the three themes underlying all this issue and all the moral risk that I discussed are shared by all models, right? So here is the tendency for homogenization in favor of majority modes, and this stochastic nature of machine learning, as well as this different perspective human and model take on what constitute a mode and how to individuate mode. Right? It is true that larger model somehow mitigate the issue. So diffusion model, because they are very big, they might have less problem with mode collapse because the gap between the model capacity, training data, training time, and the reality or phenomenon it aims to represent is kind of smaller. So we acknowledge that. But the practical problem is that because the cost to train such large model is so high, you almost guarantee there will be so much fewer of them. And each of the model we do develop will be used much widely, right? So whatever idiosyncratic biases they produce will end up have much wider and systematic effects. And we know here that this immediately offset the benefit they kind of generate through due to their size. So to conclude, we want to again seriously sound alarm for this particular massively underestimated moral risk when it comes to biases that result from mode collapse of generative models. Thank you very much. And this is my co-author, Tran. He's based in the psychology department at NTU, Taiwan. Thank you.